Welcome everybody to this talk on an overview of Compealing Code. My name is Paul Lynham. I'm the President and a Fellow of the Institution of Analysts and Programmers, which is the leading institution for people involved in the development of software. And our goal as an institution is to improve software for society. Compealing code is an interesting topic, which is all to do about the quality of software. And when considering compealing code, it'll be examined using these questions: what, who, where, why, when, and how. And hopefully at the end, you'll have an opportunity to ask any questions. So if we consider what are the abilities of source code? Well, at the bottom level, you need to be able to recognize characters, whether these are on a screen or on a printout. And this is almost taken as granted, as long as the font and the background colors are different, so you've got a contrast. You can read what is in front of you. The next ability up is readability, which is the ease with which the reader can understand the written text. So if you're looking at source code, you can say, yeah, I recognize this is sequence, or this is iteration, or this is branching. The next level up from that is understandability. So you look at some statements and you think, yes, I realize what the intention of the program is. And at the very highest level is believability. So you've read the code, you understand it, and yes, you've got confidence that the code will run and behave exactly as it's laid out. And this model assumes that you ascend from one level to the next. My own feelings about this is that you can have different abilities of the software occurring at the same time. And I'm just going to look at three properties of software. I'm going to say that, yeah, we'll take it for granted that it's legible and it's readable. What is important is that it's understandable, and that should really be the bottom layer. But in fact, there's three things that you need for code to be good. You need to understand it, which is comprehensible. It should also be well written, so it's structured well, it's easy to read. And lastly, the believability part is what I've called compelling, so that you are convinced that the intent of the code, that when it is run, it'll do and behave exactly as you expect. Now, you can get any of these abilities on their own, but what you want to do is get all three of them, which is the sweet spot in the middle where they overlap. And this is what I've called compealing. It's a portmanteau built up of the three words: comprehensible, compelling, and appealing. And compealing code, therefore, is easy to understand, it's a pleasure to read, and it's compelling, i.e. you are persuaded of its behavior when it runs. Who? Well, compealing code is primarily aimed at coders, but it's also relevant to other people. For example, anybody who writes and maintains scripts, and that could cover testers or anybody else involved in DevOps. It'll also be relevant to stakeholders who are code literate, and anyone else who's interested in or maintaining quality software. They could find this concept useful, perhaps in laying down standards and workflow procedures. And during my over 40 years now of writing code, I've found that it's paramount to write code that is maintainable. So where does this fit in? Well, Compealing Code has been specifically developed to improve the coding phase of software development. I've written a fair amount about an idea that I have called FURST, and that's an overarching framework, and that utilizes Compealing Code. So we can see from the bottom we've got FURST, which contains Compealing Code. Both FURST and Compealing Code concepts are aimed at the coding phase, but they could be potentially transformed, so they could be applied to other development parts of the development cycle, such as architecture and design. FURST is concerned with both external and internal quality, whereas Compealing is focused on internal quality only. And just to remind those who know a little bit about FURST, FURST stands for fit for purpose, unit tested, reviewed, standard, and those are all done in a timely manner. Well, there's two perspectives on quality. There's the external view, which is seen by the users, and there's the internal view, which is seen by the coders. The external view is what we call the functional quality, which assesses the compliance or conformity to a given design based on functional requirements, i.e. its fitness for purpose. So testers will test it and say, oh yes, it meets this requirement, or it behaves like this, that's acceptable. Whereas the internal view is the structural quality, and that assesses how it meets non-functional requirements, often abbreviated to NFR, that support the delivery and the delivery of the functional requirements. So these are often called the abilities, such as reliability or maintainability. And it's this part, the maintainability of code, Compealing Code is concerned with. Now, there are standards such as the ISO IEC 25000 series, which has evolved over the last 2 decades. And they are mainly concerned with the external view. Really, it's only the maintainability category which really applies to the internal structure. So as you can see, they group it by functional, suitability, performance, efficiency, compatibility, usability. It's a lovely term, isn't it? Reliability, security, maintainability, and portability. So with Compealing Code, it's this maintainability category, which is broken down into other abilities as well, as you can see from the diagram. However, what we are interested is in this maintainability, and that relies on a quality system. Now, to get a quality system, you need 2 things in place. You need quality assurance and quality control. So think about quality assurance as assessing the product after it's been made, whereas you can think about quality control as the processes in place while the item is being made. Now, they may not be the actual definitions, but that's often the way I think about these things. So I can think of 4 things that can be used in quality control when producing software. And the first one is reviews. So you can review the code that has been produced. And this reviewing process really sits on the borders of quality control, because it's after you've written it, and somebody, hopefully you'll get a colleague or more than one colleague to review your code, read through it, make sure there's no bugs in it, that it conforms to standards, and so on and so forth. And that is often done before your code is merged into the main branch. There's also tools you can use, such as static analysis tools, which will look at the code. It's a little bit different from, say, your quality assurance, where you'll run the code up and then look at it. Static analysis just looks at the source code, and that will do mainly two things. It'll give you a bunch of metrics which can be useful, such as average number of statements in a function. And these can be useful. They are sort of markers of how good or how poor the code is. But then they can also come up with some more practical hints, such as, you've defined a variable but you've never used it, or you've defined a variable and used it but you've never initialized it. So these are things that may cause bugs further down the line. Now these days, compilers, if you're using a compiled language, they've become quite good at giving you hints and warnings. But what you've got to remember is that a compiler's main concern is in compiling the program and not finding problems in your source code. So you really need to use a static analysis tool to get the best results from that. You can also create unit tests. So there's two approaches to this. The first approach is called test-driven development, where you write a test and then run it, and it fails. And then you write the code so that the test then passes. The other way of doing it is to actually write a piece of code, say a function, and then write a unit test to prove that that function works as expected. Whatever way you do it, the unit tests really are just testing the software at a very low level to make sure they do what you expect it to do. At the heart of quality control should be compealing code, because this is done when you write the software. Why? Well, its aim is to improve the quality of the software at the point of production. And this should result in easier maintenance, less defects. The software should become more reliable, and it will increase trustworthiness. And the saying says that where quality leads, productivity follows. Now, in the blue box, it is talking about product quality in general, but I think this is also very applicable to software. So it says better quality sets the product apart and increases sales. It also results in lesser defects, increases production efficiency, reduces replacement and repair costs, and increases overall customer satisfaction. The decrease in defects and repair costs decreases the input cost and increases the overall productivity. In fact, better quality serves as the best advertisement through word-of-mouth advertising by satisfied customers, and decreases the cost incurred in sales and marketing. So, in my view, productivity often follows from a quality product. You've got to get the quality right. So why is it important to write compealing code? Well, years ago, software was often developed using what they call the waterfall method. And this is where it was split up into several phases of the development cycle, and each phase had to be completed before the next phase started. So you'd get the requirements, you'd carry out some sort of architecture and design, you would then do the programming, and once that was finished, you'd do the testing, and once that was finished and any fixes applied, you deploy it, and then you'd go and you'd do your maintenance. And typically these sort of cycle lengths could be anywhere from 6 months to several years. These days, there's an increase in the cadence of development, so things have speeded up. And certainly in an agile way of producing software, you have this constant cycle that's going on. And this is why this infinity symbol is used to show a typical agile cycle using DevOps. So on the left, you've got development, and on the right, you've got operations. So you start off in the planning phase, and the plan here is your requirements and your analysis, and then you do your coding, and then all the code's gathered together and the project is built, and then it's tested, it's released and deployed into one or more environments, for example, a test environment, and eventually it'll go into a live environment where it's operated by its users, it'll be monitored, and then it'll give you feedback into the next things that need to be done, but you go back into your planning again. There's a thing called DevSecOps, and this uses the idea of applying security to the whole development process. Security obviously is extremely important, and it's become much more important, especially in the last decade. So the idea of DevSecOps is that you apply security to every stage. So for example, in the planning stage, you will most probably have a look at the threats. What actors do we have in the scene? Are they state actors? Are they individual? How are they going to attack? What are the vectors of attack? And so on and so forth. So you'll apply your security analysis to these different stages and built in security from the beginning. So you won't actually code something and then think afterwards, oh, how can we make this secure? You think about the security up front. Now then, shift left. This is the trending concept at the moment. And what shift left says is that you need to get your quality assurance closer to where you do things. The longer you leave something, the harder it is to rectify. So what I've done, I've added some things that you can do at different parts of the development stage. You can also apply things to the operation state, but I've just done the development cycle in this case. So with your requirements, your architecture and your designs, you can get those reviewed to make sure they're what you're expecting, what is needed. With your coding phase, as we've seen, you can do your reviews, you can do your static analysis, unit tests, and of course, compealing code is as you write the software, making sure that the code is written in a compealing manner. But also in the build phase, you can do a static analysis across the whole of the repository or the code involved in the particular project. You can do some analysis of that. If when you're building it, you can run the unit tests that have been written in the coding phase, and you can also review your build scripts and the results of the build. And similarly with your tests, you're going to produce test scripts, those can be reviewed. So this idea of left shift is that in the olden days when you had the waterfall method, all the testing was always heavily slanted at the end of the waterfall cycle, as you can see in the blue. Whereas these days, what you want to do is you want to put more emphasis on where things are done. So it's done in the planning and design stage and the development stage. You'll still do your regression tests, your integration tests, your system tests, and so on. But you'll need to do less of that because a lot of the testing has been done up front. And then it'll be even less to do in the release and deploy stage. Now, there's a rule of 10 in software that says the cost of finding and fixing defects increases 10 times the further into the software delivery cycle you get. By adopting a shift-left approach to quality, you can catch critical application errors before they reach production and limit the cost to your organization. As an example, if you get a requirement wrong, it's easy to fix it if you're still in the requirements phase. You can alter it. However, it gets into the coding phase, it'll take 10 times the amount of effort to rectify it. And the further on you go through the cycle, it increases by 10. So if you catch it at the testing stage, it could be 100. If it's in the release and deploy stage, it could be 1,000. And if it gets into operation, it could cost up 10,000 times the amount that if you'd coded it at the planning phase. So this is where compealing code really comes in. It's catching things and putting things right as you're actually writing the software. So here is a cartoon. I'm just going to give you a minute to look at that. Now, some of you may think this is ridiculous, but this sort of thing actually happens, and I've experienced this myself. I was once asked to review a colleague's code, and I looked at it. I found it very hard to understand, and eventually I realized what he was trying to do, and I was able to reduce 200 lines of code into 12. But this is typical. So what we've got to do is we've got to get these compealing skills into people so they write good code from the outset. So why is it necessary to have compealing code? Well, code is read many more times than is written. The largest part of software production costs comes in the maintenance phase. There's been a lot of research over the last 40 odd years, and there's been so many studies that have shown the maintenance stage takes between 65 to 75% of the costs. So it's easier to be confident about compealing code. It's quicker to understand, review, and locate any defects. Code that is poorly written is hard to read and understand, and may be difficult to spot where there are defects and omissions, and be sure that the program will behave as it's expected to when it's run. And you think about this. If it's your own code and you come back to it in 6 weeks' time and don't understand it, then you have a problem. Well, when should this be done? Well, compealing code should be applied from the start, from new work through to maintaining existing code. When you're adding new features, rectifying omissions, fixing bugs. In fact, whenever you touch the code, you should leave it in a better state than when you found it. And this is called the Boy Scout rules. Boy Scouts go into the environment, into the countryside or the forestry or mountains or whatever, and they take away their own rubbish. And if they find somebody else's rubbish, they'll take that away as well. So this idea is whenever you touch code, you should leave it in a better state than when you found it. How is this done? Well, you could most probably write a book on this section, but I'll cover some of these points very briefly. To make code comprehensible and appealing, you really need to make it self-documenting. So it reads like English. It almost speaks to you as you read it. To enable that, you need to use a good naming convention. A typical one is to use nouns for variables or fields or properties, and then use verb and noun combinations for methods. As an example, in a payroll application, you may have total gross pay as a variable, and you may have calculate total gross pay as a method. So there's no hard and fast rules, but what you need in wherever the organization is that you produce the code for, you need to have standards and you need to stick to those standards. When you're writing methods, they should be short and well focused. They're doing one thing only, and they shouldn't have any side effects. If you see a function that does several things, then that should ring alarm bells. If you see a function that is 60 lines long, that should ring alarm bells. In fact, there's a thing called extreme functions where you shouldn't write a function more than 4 statements long, but I'm not going to go that far. A good idea is to try to split these into 2 types. You have a query and you have a command. A query just returns something. It shouldn't do anything else, so it shouldn't produce any side effects. Whereas if you want to update something, that should be a command. The number of parameters is important when you're writing methods or functions, because if you've got a good method name, you read that very easily. But when the human brain comes to reading parameters, they have to stop and examine them. What is this parameter? What does it do? What type is it? What are the constraints involved in it? And so on and so forth. So it's much harder. So the less parameters you have, the easier something is to understand. So you should aim for 3 or less parameters. Contracts and defensive programming. Well, a contract is saying that if you provide these values or parameters of these types in this range or with whatever the constraints are, then this function is contracted to give you a result of this type in this range or whatever the constraints are. So it's a contract between the user of the function or the consumer of the function and the function itself. And defensive programming is looking out for things that can go wrong, so that you can test that any parameters passed are of the right type and value and so on and so forth. And you really need a strategy for this. Instead of, say, testing at the function level, if you're using properties of a class, you may want to do all your defensive programming in the setters. So when a new value is assigned to a property, you check there rather than do it in every function. But that needs to be, again, in a standard and a strategy for the organization. You want to aim for loose coupling and strong cohesion. So loose coupling is often in metrics, this is called fan out. How many other units or modules does this code depend upon? The more it depends upon, the tighter coupled it is. You've got to have all those other units for this to work. So you want to have loose coupling. You don't want to be dependent on many things. And strong cohesion means that it's well focused on one thing. So if you're dealing with say a person object, all the methods are only to do with a person. They're not doing anything else or on any other type of object. Solid principles are a good set of rules to abide by. So these stand for single responsibility, open close principle, Liskov, interface segregation, and dependency inversion. I'm not going to go through those, but you should be able to look those up if you're not familiar with them. And lastly, another good idea is to utilize design patterns. These have been well catalogued over the years. And if you use the name of the pattern, people are familiar with it. So for example, the iteration pattern, normally you have like a first, which will give you the first in the collection, and then you can do a next until it comes to the end. So those type of patterns are well understood, and when you see them in the code, you understand them straight away. You know the meaning of them, you know their advantages and disadvantages and so on. So code becomes more comprehensible and more appealing if you use design patterns. So to summarize, compealing code is a powerful concept, and hopefully if you follow this, it'll produce software that is easy to understand, it's well structured and pleasing to read, It persuades the reader that it will behave as intended, and it will then have the benefits that the software can be easily maintained, and this is important these days with more frequent release cycles. It fits well in with the current emphasis on left shift. Remember, moving your quality assurance closer to where the product is produced, and it leads to reliable and more trustworthy software. So that was an overview of Compealing Code. This has been produced with the Institution of Analysts and Programmers, the leading institution for people involved in the development of software. Our goal is to improve software for society, and you can see our contact details there, our website, our telephone number, and email. Thank you very much for attending this presentation.